Hey guys, how's it going? Welcome to another episode of Ferris Makes Demos. This is episode 39, and it's a bit earlier than normal. I ended up making some plans this evening, so I thought I'd move the stream to a bit earlier time today, just to see how this works out. I mean, this is a more casual stream anyway, so I don't think you guys would mind too much. I called this Floating Point Woes, so what I'm working on, if you guys tuned in last week, I'm preparing WaveSabre for our official release. Again, I'm not revealing when that's going to happen, but at some point we're going to do a music disc and a bunch of stuff for that. So that's what I've been working on lately. And yesterday, one of the things that we've done with the synth is we've avoided SSE, and this was due to some linker issues that we had, where we relied on some SSE implementations of functions that weren't available in the Windows standard msvcrt.dll. However, I would like to actually explore using SSE again for a couple reasons. One of them, the compiler should be able to auto-vectorize a couple of our things. I don't know how much we'll gain from that specifically, but there should be some room for improvement there. We also should be able to vectorize stuff ourselves, although that we probably could have done anyway, because we really just want the compiler to generate SSE code for the synth. Another one, though, is that we can actually avoid denormals altogether by setting some SSE flags that treat denormals as zeros, which should allow us to clean up a bunch of the code while making things a little bit faster, hopefully, especially for denormal cases that we missed. So what I started doing is I went into the synth and hold on, let me zoom in a bit here. That should be enough. Basically, what I did is I just went into the settings of all of our synth stuff, all of our different projects, and I started just changing the code gen settings here to using this enable enhanced instruction set field to not set from IA32. This should allow the compiler to use SSE, AVX, whatever it needs to use. Ideally, it'll probably use SSE or SSE2. It seems that that's what it's doing when I'm actually looking at the generated code. And from there, what we end up with is mostly the same stuff, except, let's see here. I'm just going to exclude this really quick, and let's see what this does. There we go. So if I try to build our player test for the synth now, with now using SSE code, because we don't link to the modern, or the actual MSVCRT, the versioned one for Visual Studio 2013, the compiler has generated some code that relies on these SSE2 implementations of cosine, pow, and pow-f. But again, because we don't link to the right CRT, we link to an older one, these aren't actually there. So we need to provide our own implementations of these. Now, the way I've done this, let's see, just remove this. And then this should build now. So I've done this, so I've just implemented these myself. So I went in and I looked in a debugger. In fact, I'm using X32DBG, which I guess is part of a package called X64DBG. I also use OllyDBG, but really they basically behave the same way. So if I go ahead and open, actually I won't open this one because I did this in an isolated test project. Here I just called SSE shiz. It's basically the same thing. It just has this main that does a few things here just to test a couple functions, cosine, pow, and pow-f, so the same functions that we're actually missing in the synth, and then tries to implement some polyfills, or not polyfills, but implementations of these. So, for example, if we generate some code here, have that build, and then I'll just open that in X32GBG. If we go in here, so I'll hit run here, so it actually goes into the main CRT startup function, which I guess there's a breakpoint here automatically. I'm not actually sure if that's the case, but that's what we're doing here. And then we need to step a while, because this isn't our actual main. This is the MSVCRT main CRT startup function. And if we go down here, eventually there's going to be a call to here, SSE-shiz.main, and that's our actual function. So then we're going to step into that. And here's our actual main function. So here we see there's some prologue stuff here. It looks like the typical push base pointer, move stack pointer into base pointer. Mask off some bits from the stack pointer. I'm guessing this is just to align things to a certain boundary and also allocate some stack space in a fast way. And then here we see a move SD. So this is going to be a double word or move single double word into an XMM register. Actually, can you guys see this very well, or should I probably zoom in here if I'm able to do that? Let's see. View? No, I guess not. We're going to have small font today. So anyway, so this just moves a constant into here and then allocates some stack space to call libm sc2 cosine. So again, this is just the names of these functions that the compiler generated code to use. And then because we've provided them in this other crt.cpp file here, it will actually call into these instead. So if we just follow this a little bit more until it gets down here, you can see this move SD moved a value into XMM0. This value presumably is pi times 2, which this looks like some crazy number, so it probably is. And then allocate some stack space and call this libm sc2 cosine function. And we can, oops, I stepped over it, but that's okay, because we'll just step into the next one. Whoops, I did step into when I didn't want to. Just step through all this crap. Here's a ret, there we go. I'm mixing up the buttons here because I'm not that used to this one, but here we go. So here we jumped into libm sc2 pow, which of course is part of our code, so just jump down here. And then this is my implementation of pow. I lifted some of this from online because it's fairly easy. I'm just actually relying on FPU instructions to do this. So for example, we can look at my libm sc2 cosine function here. And instead of using a fast lookup table or something, I just went for the simplest possible implementation, at least to start with, because that's what I want to do is I want to get this working first, and then we can look into optimizing it with actual stuff. So cosine's really easy. We allocate some, it takes a double and returns a double. I made it naked so that we just do the entire thing in ASM. Which is just a little bit easier for me, I guess. And so we're going to allocate some stack space so that we can transfer, like we expect this argument to be in XMM0, seems to be what this does. So we're going to allocate some stack space to go through the stack pointer in order to load it into the FPU. Then we're going to call this fcosine function, which is going to calculate the actual cosine. We're going to move that back onto the stack and then back into the XMM0 register, so it'll be ready to be returned. And then we're going to deallocate that stack space in return. So very, very basic function here. The POW ones get a little more complicated. The main parts here, if we just look at these, so again, these are also naked, and here we take in X and Y, which are passed in XMM0 and XMM1. X is the base and Y is the exponent in this case, and then we're going to return whatever that value is. A couple things here that make this a little more complicated. We don't have FPU instructions and, of course, SC instructions that can actually do exponentiation like this. So what we have to do is we have to translate it into a different form that the processor actually does have instructions for. Now, I kind of just blasted my way through this, and it doesn't quite work. It works in some cases, and what I hope to do today is actually debug some of those other cases. And the way we'll do that isn't the most straightforward, but the main idea here is that this seems to work in most cases, but there are some corner cases that I've clearly missed that the synth is using that's causing us some problems. Basically in the form of things being unstable and then the audio just making a pop and it'll be done, or instruments not being able to be heard. And the way I'm going to debug that is actually I'm going to dig into the song files and figure out which parameters of which instruments are actually causing the issues in order to isolate the exact corner cases that we need to care about in this POW implementation. But the main idea here, I need to actually look this up in our Slack here. Because we actually have to do a different form here. So if you take x to the power of y. Now remember, we can't do exponentiation like this. Hold on, where is my hat? There it is. This is actually it's exactly equivalent to a form that looks like this. We can take some base raised to the power, I'll abbreviate base to b because it's actually arbitrary. And we can take some base and raise it to the log base of x times y. And I think you can get this just with basic logarithmic identities. But the idea here is that we'll do this log b as well. We can basically have any base here, and this will still be accurate, or at least equivalent. Particularly, the useful one we have is this log base 2 of x and then 2 to this power. So then this is called exp2 because it's raising 2 to that exponent. So we have exp2 and log2 are kind of our most important things. Now, as it turns out, the x87 FPU actually has instructions to do exactly this and exactly this with some caveats. This instruction, I believe, is called, if we look at the code down here, I believe this is FYL2X, which does this part basically automatically. So all this thing is doing, it's doing some special case tests, and I'll get to that in a minute. But it just loads from XMM0 and XMM1, the actual arguments. It loads those into the FPU stack and then does this. And the next thing it does is it prepares stuff for this exp2. Now, it can only do exp2 if the value as input is within like 0 to 1 or something. I don't remember the exact range, but you can look up the instructions that do this. And that's what this F2XM1 thing does. So what we need to do is we have to basically extract that fractional part of that exponent before actually raising it to this and then scaling it by whatever we took out of that later. It's a bit confusing to go through this, so I'm not going to go through that in too much more detail, but that's basically all we're doing is this form with FPU instructions. Now, it appears that alone actually covers most of our cases as I sit here and just play with this. But as you can see, I started doing some corner cases, like if the base is 0 and the exponent is 1 or, weird stuff like that, and trying to make it equivalent. So I have basically the identical project to this one, but without my own custom implementations. And if I run that with the same values, we get sort of these results, and I'll run it with our own implementations here. Although I think it didn't build just now because it's running in the debugger. So I'll just stop that here. And if we compare these, I think they're identical in these three cases, 101, 101, which is really good. We want these to be identical. But it seems to be that when I actually put these in the synth, they're not equivalent. Oh, by the way, the extra code up here, what it's doing is it actually checks for a couple special cases. Basically, it compares, it zeroes out XMM2 and then uses that to compare with the exponent or the base, and then returns 1 or just the input value, depending on if either one of those is 0. This seems to work for cases that I've discovered, but it seems that there's again corner cases that I haven't considered. There are a few different implementations of this floating around online. It was kind of hard to find just a drop-in one without a lot of tables, so I might just end up ripping a different one or using something else or coming up with something different. But for now, I just want to see if it's a quicker win to be able to go a little bit further with this approach, because it seems to be okay. Mad Process, thanks for the follow. Really appreciate it. Also, do I even need this light on? Because it's warm in here. No, we'll just do natural light. So yeah, so this exact code, when I put it in the actual synth, works for the most part. Let me see if I can actually turn this system audio on. I'll shut down my Spotify in case I play something. So I've literally put that exact code in the synth. Cosine works perfectly. This has no issues because it's pretty much trivial. And then POW and POW-F, the only difference, by the way, between POW and POW-F is whether or not the arguments are doubles or floats. So 64 or 32 bits floating point values. And the only difference there is that I'm using like XOR pack double instruction here or XOR pack single instruction here. And other than that, they're actually identical. Dusty says, if you have so much trouble using the old small STD lib, maybe use the newer one. No, because this is for 64K, where we can't rely on anything that's not basically installed on vanilla Windows to be there already. So we can't rely on the Visual Studio runtimes actually being installed. Otherwise, this wouldn't be a problem, and that's what we would do. But we link to the old one to make sure that this can actually run on a clean Windows install. The other way to avoid this, of course, is to not use SC, and then the compiler will actually generate FPU code to do all this, which is fine enough. But then we have some speed and denormal issues, which we like to get around. So this is kind of worth doing. By the way, I forgot to say hi to guys in the chat. Cluwash, Zakwar, Sagittac, Sandals, Desu Used, Mr. Toe, Provad GL, Winter Squirrel. Good to see you guys. Also, I'm a bit surprised to have 35 viewers this early in the day, but I'm really happy about it. So thanks again for that, guys. But yeah, so if I play this, I don't know which song I have running here. Okay, it looks like it's Varia, if you guys have heard that track. Hey, Dino Colin. I'll turn that down a bit. Hey, Joe Fish. So this track seems to work pretty well, except right about here, you guys might not know this, but there's a riser that's missing. It's supposed to just go behind this, and it's just gone. Arusius, how's it going? And then here, this sound sounds almost exactly like what we want, but not quite. That might be fine, though, because I know that Hoffman did some touch-ups to this track recently. And then pop, and it's dead. And I don't know why that's happening or where it's happening. This, I don't think, is the best example song to actually start debugging this, though. This was just when I was trying to isolate some of these corner cases, but those didn't seem to cover enough. I was able to actually improve it by adding these corner cases, but it's not quite what I need. So what I'm going to do is I'm actually going to go and convert a different tune. In particular, we'll do Elysian, which you guys should all know and have seen that demo by now. Nah, just kidding. But anyway, so I'll just convert that, and then I'll start this player test again. Now it should play Elysian. And things seem fine here. Turn that up a bit. There's an instrument missing there. There, Colin, I totally could use a reference implementation and then compare epsilons to that, but the issue there is that I don't know which corner cases I need to test. But I guess if it's like floats, I could test quite a large range, at least random stuff. But we'll see. What I think I want to do now is just see if there's some obvious corner cases by going through the actual project file, because we know which stuff is actually going to be, like, we know which stuff is missing. So I want to actually look at different parameters. Maybe this isn't the best approach, but that's at least what I'm hoping to do today. Jeffrey says MIDI-based format. So yeah, there's a MIDI-based format here internally in the synth and the replayer. I have a video on WaveSabre in particular, which is the synth that I'm using here. So if you check that out, you'll find that answer specifically. Let me go ahead and find our Elysian project here. I don't want to show my Explorer window as I'm searching projects because there's some new stuff in there. So this is the final of the Elysian project that we're going to have in the music desk, I guess. It's this ringy thing that we're missing, which I guess is this. So what I can do here, this is kind of cool. I can take this loop point here and just have that. And I'm actually going to delete a bunch of the other stuff too. Now this is in our shared collaboration folder. So let's see, the output of this should go to kickduck. So I'll just get rid of like everything else. Actually, I'll send this to master too. Get rid of this. We should just have that. And then what I can do is I can save this out. As a debug file. And then what I'm going to do is convert that. And it should, of course, not work. So I'll run that. and then run this player test, and we should not hear anything. I actually hear a tiny bit of noise, which is interesting. You guys might hear it too. You said, how does this mess here sound? This is actually, I think, Ableton Push. This is Huffman's Ableton Push did this, and this is this stuff. So much MIDI, but it sounds great. That funny? Oh, I love this stuff. So what I actually want to do here first is I'm just going to mute a bunch of this stuff. Just get a basic tone there. Now, if I save this and then I reconvert this, I hope to hear the same thing. What we're trying to do here is isolate which part of this chain actually messes everything up. Okay, so it's already in that original synth that this gets messed up. In this original Falcon here. So I would guess we might actually start isolating code in Falcon to find out where this is. Whoops, I actually don't know if I saved this. I think I did, but I'll just make sure. We want to double check that. Doesn't hurt. And also, by the way, when I run the converter, it tells me that it skipped a bunch of devices, which is good because these bypasses are enabled. So we want that. And then set that as startup, and yeah, we just get crap out of this. So that's fine. So let's go ahead and go into the Falcon code here. Falcon is our FM synth in WaveSabre. And I'm actually just going to go to run here. This is run for a single voice, actually. And I think what I can do here is I'm just going to look for certain things here. There's some vibrato stuff, fixed denormal, volume to scalar. This might be something. Panda scalar, because I think I'm looking for stuff that uses POW eventually. And okay, this one doesn't. Panda scalar I don't think does either. Uses square root, but that should be fine. Here, this ratio scalar thing here. This does POW here, actually. I'm actually just going to remove this term and see what happens here. If we just play this. And there we have a tone. So that's actually pretty interesting, because that to me says that that POW is what's actually breaking here. So what I think I want to do is try and figure out what this is going to be. The inputs to this function are actually going to be. Cool, I'll just copy a big ass pad. Is that what that was called in Ableton? Because that's really likely that that's what this was. But yeah, so let's see. If fine, this fine parameter here, if we go to ratio scalar, OSC1 ratio fine, OSC2 ratio fine. These, if we go up here and look at the ratio fine and OSC2 ratio fine, they're both at 0.5. And if we actually look at this in Ableton, pull this editor up here, it's these ratio semi is what it should be. And these look like they're 0.5. That's what those actual values should be, just from here. And so it looks like those are actually unchanged. And this goes ratio coarse and fine. Coarse doesn't matter, it does some floor stuff, and then fine is the only one. So fine minus 0.5 is 0. So this would be 0 times 2 to the power of 3, which I guess would be 0 to the power of 3. So if we pull that over to this one, this should be that case. And in this case, we get 0 out of this one. And in our SSE version, if we do the same thing, we also get 0. That's not very good. Yeah, Colin says, sorry, I missed the start. You're trying to optimize the POW function by making it smaller? No, we're actually trying to re-enable SSE in the synth. And to do that, because we link to MSVCRT and not the actual runtime MSVCRTs that this particular Visual Studio version expects, we need to polyfill some of these functions. So that's what we're working on here. So I think this was unfortunately not very informative, which is a bit of a shame. It may be, though, that this was like a very small number that wasn't actually 0. I doubt it, though, because this should be easily representable. But we could try this actually. So these os ratio fine things here, they're floats normally. And in fact, this POW function should be doubles. So if we do something like this, 0.5, and then we do times 2. Oops, I have some float there. I'll do that. Still getting 0 out of that, and I'll just copy this to the other one. Although I expected this to be the same. Still 0 there. Falcon Lover says, why don't just print the values? And that's because in the context where it's actually running in here, we don't have the ability to print those values. But we should actually, in the replayer, at least be able to print some of these. So let's try that. Let's do... Oh, in this case, fine is a double, but that should be fine too. So we can import printf here, I think. Should be okay. We're going to get a lot of these because I believe this happens once per frame. But yeah. So what we should be able to do is print f. And I think it's f that we want. So we'll do fine. And then make a hole there. And then base. And x. Then we'll do the base for this, and then the x here. And that should give us some information at least. So if we run this, okay, so this is interesting. The subtraction seems to have given us -0. Sometimes 0, sometimes -0. That's a bit odd, but I'm not too concerned about that. What I am concerned about is I want actually the result here. Now this, of course, is going to be the result of our version, our implementation of POW here. Which I'll calculate there. And we got some nans, so that would make a lot of sense, actually. So it looks like when our base is -0, we get some nans out of this. That's concerning. I wonder why that is, actually. But this is definitely the problem, I would imagine. So let's actually try and set this up here. Or actually just in our SSE one here. So this... Make this double again. It looks like we should just be able to do -0.0 and then 3 here, and we should get something messed up. Here we get is -0 actually, which is a bit concerning. Let's see. Oops, that's also the wrong input there. Or was no, we do some double here. Okay, that's actually, let's get rid of this. Anyway, we got -0 as the output there, whereas in the no SSE version, we'll set up this basically the same thing here. Gonna bump the font size here too. And there we also get -0 out of this instead of 1 dot number sign qnan 0. That's a bit odd actually, because this should be the same base and exponent. I don't know why this would result in different code. Also, regular 0 to this power should give us 0 as we would expect. Now, I would suspect the -0 in this case does actually generate the equivalent number that we have. But we could also do this. Double fine is 0.5. And then we can do double base is... We'll do actually the same thing here. This should, unless these are constant folded, which we can actually check in the output code, give us the same stuff. Here we got 0.5, 0, x is 3, and res is 0. That's somewhat interesting. I wonder... This looks correct for half these cases, but these other ones we had, again, -0 for the base. It seems to be alternating. I wonder why that is, actually. In the Falcon code here, ratio to scalar happens twice every frame. We have this coarse and this fine. Now, the fine ones should be both about 0.5. Maybe they're not equivalent here. Yeah, that's a good call, Daniel Collin. If we try, I guess something like this will do it in that case. I didn't seem to do enough. Oh wait, we want the other way. There's some really low number here. I'll do even more out here. And then we get base for -0, and our res is -0. That's somewhat interesting. This again is in the no SSE shiz. So if we do this in the SSE one, which is our implementation, I'll just pull this here. Then we get some nans. Okay, this is actually great. So then we've at least isolated one case that we know about. Very interesting. So again, if we just wanted to isolate just this, the way we would do that is, as Daniel Collin pointed out, some really small negative number that's not quite 0 raised to, in this case, the third power. And there's our isolated case. So, nice call on that. By the way, I'm only going to be streaming for about 20 more minutes, just so you guys know, but should be okay. So, if we look at this code here, I might actually end up doing a test suite for this implementation just to play with this, but I believe, so the first thing that we're going to do here is check that our base or exponent is 0. This is definitely going to fail because this is not going to be close enough to 0 for this to matter. So basically it needs to be 0 or -0 for the actual equality test with this compare to actually give us equality against 0. So neither our base or our exponent are 0, so then we have this actual code that's running. In this case, you know, I actually can probably step debug this and see what happens. In fact, I'll do that. So this SSE shiz, so we can actually go into x32dbg and pull this up. So we'll run this. Again, we'll jump into our code here, step over until we actually get into main. I don't know how this debugger works with different sessions, like if I add a breakpoint when it calls main, if that will actually be preserved between runs, because I think the actual code itself is going to move around a bunch in the binary, but it doesn't matter too much that I'm just clicking through this. So we want this one here, this libm sc2 pow to be the code that we break into. That'll be this call here. XMM0 is going to be this value, and XMM1 is going to be this value. So we'll go ahead and step through that. And as we go through this, XMM0 has some crazy value, which is what we expect for some really small number like that. And step once again, and XMM1 has a more cleaner looking value, which we would expect for the number 3. And then we actually do the call to the POW implementation. So here, this is the exact code that we had earlier. We can start stepping through some of this stuff. So what this is going to do, again, is going to allocate some stack space just to transfer values to and from the FPU. It's going to zero out XMM2. It's already zero in this case, but that's just so it can do these comparisons it's going to do. So yeah, it compares XMM1 and XMM2, and then it should set the flags here. 0 flag is 0 and whatnot. So that means that these were not equal. And so it will not do this branch or jump not equal. So it will do this branch. And then it's going to compare the exponent as well, which should also fail. So here it will jump equal, but it won't do this branch. And so now we're going to move things into the FPU registers. So we should be able to see those here. And we're going to just move them straight into there. So here we have our, 3 here, and then this really tiny number for the base in R6 here. Or actually, this is ST0 and ST1 here, due to the way the stack actually works. So first it's going to do this FYL2X. And that gives us a special nan. That was quick. That already is probably what's happening that gives us this problem. So I want to actually look at FYL2X and see if there's any range issues that we have to worry about with that instruction. I wonder even if it just already has issues with negative numbers for the base, because I believe that's what this was, that the base was really tiny and negative. So if I just Google that instruction, we can see it does compute ST1 times log base 2 of ST0, stored the result in ST1, and pops the FPU register stack. So basically it replaces ST0 with this value. Replaces ST0 and ST1 with that value in ST0. So we have a couple things here. Divided by 0 exceptions master register ST0 contains plus minus 0. The instruction returns infinite with a sign that is opposite the sign of the source operator register ST1. Don't think that's terribly relevant actually, because we already handled that case. But I think here, let's see. Yeah, here, it must be non-zero positive. So already, the fact that it's negative is going to be a problem here. Now, what's interesting, actually, is that the reference implementation here, in this case, when it was negative, this gave us -0. I actually wonder if we give this just a random negative base. So if we give... -1 to the power of 3. What does this do? Then it actually gives us -1, which is correct, by the way. If we give this -3 to the power of 3, what does this give us? -27. I wonder if we can strip the sign before we do this and then do the POW normally and then replace the sign. I don't think we can, because like if we do this by 2, this is going to be a different number. Then this should be 9 positive. That I don't like. And I want to actually match this implementation. So if nothing else, we've discovered that at least it's the negative numbers that this will fail on. I guess what I would actually want to do in this case is start fuzzing this now that we know that. Or maybe debugging and seeing what the other implementation is going to do for this. Because I think you get some weird cases if you do like 2.5 for some of this stuff. Yeah, then we just get some ridiculous stuff. And that's not good. Yeah, exactly, disuse. That's what that's what I tried to demonstrate there, is we end up with weird stuff where we have a negative base to a fractional exponent. Crazy stuff happening. There is an alternative thing that we can do here, by the way, as a quick fix, just to see that our stuff is right in other cases. And that's actually this. We could just take this POW thing here. I think I have a clamp, which I don't think that's the clamp we expect, actually. Yeah, we want a clamp double. Let's actually add that. This is not actually fixing the problem. It's just covering some of the symptoms, because we shouldn't really have these cases anyway, ideally. But I just kind of want to see if it works. And if I do that, then we can go back into here, clamp D. And I don't know what our max should be here. Oh, this actually should be negative in this case. Fine minus 0.5, because if fine was 0, for example, then we actually want this to go from negative 0.5 to 0.5 times 2. So this actually is remapping it from negative 1 to 1 in POW here, and then raising that to the third power, which I guess is something that gives us some kind of nonlinear value, but will preserve the sign. The annoying thing is we might actually want to detect, and that might be what the actual implementation here is doing, is detecting that this is non-fractional, and then having some special case code for handling this as an integer thing. So this actually won't fix the problem anyway. Let's just go back and remove that helper then. Whoops. Just use says maybe a more idiomatic solution would be to use POW-I. In this case, it might be actually. Let's see. Whoops. Actually, is POW-I even a instruction or a standard library function? It should be. Yeah, int times. I mean, the other thing we can do in this case as well, if we actually want to work around it, is even easier. And that's, we can go in here and just not use POW for this. Which is probably faster anyway. That gives the expected result at least. I'm actually okay with doing some workarounds like this in this code as we switch to our own POW implementation, as long as we keep things small, because these are kind of corner cases anyway. But we'll see how many of these things there actually are when actually fixing this stuff. So I'm actually going to go through and unmute that stuff, just see how many cases this actually covers. And this should be okay when we play this. And we'll reconvert that again. And play that. Seems to be okay. Yeah, sorry about the small font, you guys. It's something we're going to have to deal with today as I'm working at a Visual Studio and whatnot. Let's go ahead and actually convert the whole Elysian track just to see if I notice anything else that's wrong here. Sit here and chill for a couple minutes. I expect my next few Sunday streams to be a lot like this one, where I'm just kind of working on this stuff, and whatever I'm working on that particular day anyway is what we get to see on the stream. I think this is going fairly well. This is promising. Yeah, Huffman, let me know if you hear anything wrong. But so far, I think this is pretty good. This track still rules. The nice thing is, I believe this is actually faster. Might not be, though. 6%, 7% CPU. I'll have to do some proper A/B testing about this later, but... I still haven't removed any of the denormal stuff. That comes once this stuff actually works. This sounded great. I'll try another track after this, and then I think I'll stop the stream for today. Hopefully, I think there are a couple of these tracks that just would pop and then they'd be done. We'll see if we fixed any of those cases. But what's cool about this is that this seems to be working, at least, even if it doesn't work for all POW cases. And again, I don't really mind going through the synth and adjusting some of these to not rely on POW when they don't actually have to, because it should actually be a little faster to do those 3 multiplies in this case anyway. And also it helps to avoid mathematically ambiguous stuff. So I think we're okay there. Anyway, I think Rubik was another one, which is our soundtrack to Soundproof Motion, which was our demo with Fairlight last year. This, I think, just ate shit right when I started playing. Already, this sounds promising. And I wouldn't be surprised if the Fix in Falcon would fix a lot of these songs, because we use that. It's a pretty ubiquitous synth. There it goes. Did you hear that? It just pops and it's done. No idea what that is yet. And the other one that did that, of course, was Varia. There's a lot of these tracks I haven't tested yet, just because I already found problems with these other ones. Whoops, I didn't convert it again. So we'll just try this other one. But then I still think I'm going to go anyway after this. By the way, Hoffman is planning on streaming later, I believe. So DJ Hoffman, if you want to, he's in the chat. If you want to go follow him and see what he's doing later. Should be some pretty cool stuff. I think I have him on auto host already, so might just be able to stick around and see that. I don't think it's overflow the audio buffer. I think it's some NAND somewhere. Caused by some POW special case, probably. Because all this stuff works when we use just regular when we get the compiler to just generate FPU code. It wasn't until we had SSC here that it was the problem, so definitely gonna be NAND somewhere. That'd be awesome, Daniel Collin. Yep, and there again, the same symptom. Let's just try some other tracks while I'm still here. Still got a couple minutes. Engage, I don't even think I've tried. And again, we can isolate this the same way we did with the other ones, but I'll do that on my own later. Funny thing is, I never know if or when this stuff is going to cut out, so. If nothing else, though, this gives you guys an idea of how special casey stuff like POW actually is. It's pretty annoying. And I hope to get away with something pretty minimal like this, but we'll see. Exactly, DJ Hoffman. Sounds good so far, though. But who knows? And of course, it's the drops on all these. That's so funny. I'll just try Reverence now while I'm still here. And at least this, again, just like we did with debugging Elysian, I'll do the same thing with this later. Just start muting stuff. Oh, that happens right quick. Thunk. Rip. All right. Anyway, this has been fun, guys. I'm going to head out, and I'll continue working on this in my spare time. Next week, I'll probably be doing the same kind of stuff. And, of course, Thursday, I'll be back on normal streaming schedule, as this Thursday is not a Norwegian holiday. Anyway, I'll see you guys later. Thanks for hanging out.